Today, we continue the study of curves by relating the notions of length of a curve to that of the Hausdorff measure of its image. One has to have seen these before this video to be able to follow through. And the third notion that we will need will be that of a metric derivative, although you can survive without knowing it if you only are interested in the Euclidean cases. Before we continue, please consider subscribing to my channel. My data indicates that some people are following the channel, although they have not yet subscribed. The starting point will be this special case of what we call the area formula, namely that if you have a Lipschitz curve into a Euclidean space that is injective, then the Hausdorff-1 measure of its image is the same as the length of its parameterization. This is the same as variation of gamma, which is defined through the supremum of mutual distances of a partition, just to show what these objects are. And then as a third claim, that quantity equals the integral of the speed of the curve. Gamma prime exists by Rademacher's differentiability theorem almost everywhere, so this integral is well defined. We want to see today the case of non-injective Lipschitz curves. And moreover, we want to allow the target spaces to be metric spaces and not just Euclidean spaces. The image of gamma, which we will always denote by capital gamma, cannot tell us if a part of a curve has been covered twice. Here already I'm abusing this terminology curve to refer to both as the parameterization, the map from AB into the metric space, and at the same time, the capital gamma, the image of the curve. So, and this is very common terminology, the common abuse, in fact, that curves can be referred to both. And the point here again is that if you look at just the image of a curve, you cannot tell if part of a curve has been covered once or twice. Take, for example, just the circle in R2. By looking at the circle, you can't say if this comes from a parameterization that runs only once along the perimeter of the circle, or maybe it does it twice. Therefore, if we want to hope to get something similar to this, we have to take into account the non-injectivity or double coverings. And the way out will be to observe that H1 of gamma can be written as just integrating 1 along the curve gamma against the Hausdorff measure dH1. And therefore, the idea will be to replace 1, which here is just saying that every point has been covered just once. So this is only for injective curves, with some function that records how many times the points on the curve have been covered. And that leads us naturally to the following definition of a multiplicity function. If you have a curve, then for every subset of AB, this allows for more general statements. We define this function as, so there's a definition rather, the number of points, so you should read this as the number of times that gamma sends a point from E to X. So X is fixed in the target space, and then you look at all the T's from E whose gamma value equals X. And cardinality is just the number of points in a set, which could be infinity if the set is exactly when the set is infinite. There are some simple observations that I list here, but they will be very useful. Number one, that the multiplicity only concerns the image of gamma, really, although we can allow X to be outside the image of gamma, but that will only give us 0. So when integrating this multiplicity on X, it will be the same as integrating it along the image gamma. Therefore, even though X could be a large space, the integral dH1 only concerns gamma. And again, in the case of injectivity, this multiplicity is just the characteristic function of the image of curve one, if and only if you are on the image, and zero otherwise. And then this integral here is simply just integrating one. And because image of gamma, this capital gamma is compact, it's an H1 measurable set. Therefore, this is an H1 measurable function. And therefore, integral is just H1 measure of gamma. A nice theorem that also justifies why this multiplicity function is also called Banach's indicatrix. I had no idea about the history of this terminology, this naming, until I read in Leone's book about this theorem. You have a continuous curve into a Euclidean space, so it's only continuous. We don't start with Lipschitz. Then this multiplicity function is a Borel function. Notice that this is a Borel function on Rk, not on the interval. So if you are merely continuous, then this function is Borel, so you can integrate it. And once you integrated it, it equals length of gamma. And with possibility that this be some value equal to infinity. Therefore, it is in fact stronger than if we allow just Lipschitz, because it detects when a curve is rectifiable. This side is finite if and only if this side is finite, which in the language of measure theory is just saying that this function, this Borel function, is H1 integrable. This is already interesting. If we take k equal to 1, then we are used to graphing functions from interval into R in the same plane. So this will be R. This will be another copy of R. This is Rk. And then from A to B, so a continuous function is something like this. So here value B, here value at A. What the function is claiming is that this curve will be rectifiable, and the equivalent terminology is that it is of bounded variation. We have talked about this terminology before. In fact, this is commonly written as variation of gamma, especially if you are mapping into R1. So this theorem is saying that this will be of bounded variation if and only if the function, multiplicity function, is integrable. So let's look at what multiplicity function looks like here. So this, you fix an x in the target space, then you will count the number of t's. So this is one t value where gamma t equals x. So you count the number of points where, so in this case, number of times that gamma sends a point from AB into x. In this case will be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case, it will be 10. You change your x to some other value, you get something else. If you are way off, then you get 0. So the theorem says that you are of bounded variation if and only if there are not too many values of x for which this n is too large. And the precise statement is just that it is integrable. It could be infinite for some values, but as long as it is not for too many of them, you are fine. An immediate, for example, application could be to the sine curve, although there we are not defined on the compact interval, but just open 0 and 1. But this theorem, in fact, is valid for non-compact intervals. But anyway, if you have the sine 1 over x curve here, then for every x between negative and 1, negative 1 and positive 1, the multiplicity will be infinite because every point is covered infinitely many times. So the integral of multiplicity will be integrating plus infinity from negative 1 to 1, which is infinity. And that means that the length is infinite for the sine curve. How about if we multiply x into sine 1 of x, so that as you go, some x's are now covered only finitely many times. So almost every x, in fact, every x other than 0 will be covered only finitely many times, but that doesn't automatically mean that this is integrable. So it's a nice exercise to see what this says about that. So things I try to illustrate by pictures are also written here. If you want to read through them, feel free to pause the video as always and comment your questions if you have any. Okay, so what is the theorem of interest for today? If you start with the Lipschitz function and this time into an arbitrary metric space, then for every measurable subset of AB, already just E equal AB is interesting. The multiplicity integrated will be equal to integration of the speed of the curve. So what is the speed of the curve? If you are mapping into an arbitrary metric space, there is no notion of gamma prime, no notion of velocity, but there is a notion of the speed of the curve. This is only notation, just meaningless. Be careful with this. It's only a notation in analogy to Euclidean setting. I have 2 videos which discuss this notion of metric derivative. It's at the end of the day a real number, non-negative, and by some important theorems, for a Lipschitz curve, this speed is well defined almost everywhere for almost every t. Therefore, this integral makes sense. And of course, the main claim being that these 2 integrals are in fact equal. As I promised, if you don't know what metric derivative was, or you weren't interested in maps into arbitrary metric spaces from the beginning, for the case of x being just the Euclidean space, this speed is the usual derivative of gamma, and then take absolute value, here rather norm, because you're in RK. And this time, we know gamma prime exists almost everywhere by Rademacher's differentiability theorem, and therefore the speed is well defined almost everywhere. If we go back to the example of this circle, suppose we have a parameterization gamma that covers this circle twice. For example, e to I 2 pi theta. Now theta from 0 to 1 covers it once, but if you allow 2, now you're covering it previously once, now twice. In this case, the length, the integral of the derivative will be twice the perimeter, because one travel, this integral becomes perimeter of circle. Now you do it twice. On the other hand, this multiplicity is equal to 2. Maybe there are 1 or 2 points that are exceptional, but it's 2 almost everywhere. So its integral will be twice. That will be integrating twice over S1 dH1. And this will be 2 times H1 of the circle, which is equal to just the length of the circle. And therefore, this holds. So that's how the multiplicity saves the day. Now let's look at some other consequences of this amazing lemma, this amazing theorem. One corollary is that if you are Lipschitz, then because the length is finite, this means that multiplicity integral is finite. And that means that multiplicity in particular is finite for H1 almost everywhere. This means that you cannot have a Lipschitz curve cover too many points too many times. So you can have a Lipschitz curve that covers this point infinitely many times. It just keeps going up and coming back there. If you want to save length, for example, you can every time do a shorter loop. So this becomes a point covered infinitely many times. Theoretically, you can have other points with the same property. For example, in this picture, let's say also every loop goes there. And then, yeah, maybe something like this. Also here, there's a point which is covered infinitely many times. The corollary says that this will happen only for a set of values that constitute only an H10 measure subset. Can you give an example of a curve where the points with infinite multiplicity are in fact of infinite cardinality? So H1 is 0, but the set is not measurable like a counter set. That's again a nice exercise. If you know one, please put it in the comments. Another corollary of previous theorem is that there you didn't have this G, which means you had G equal just 1. And it's a very standard trick that if you prove something similar for the constant functions, then you can have finite summation of constant functions. And from that, you can extend to all, say, measurable functions. But here, just to be safe with the integrability and measurability, we take G to be a Borel function defined on the image of the curve. So here is a curve, the parameterization of some set in the metric space X. This tells you how to integrate G on the curve. Remember, this is the same as integrating on the curve. And it says that if you have a Lipschitz parameterization, you can pull back the values of G, which is defined on here first. You can pull them back to values of G composed with gamma T here. And then if you integrate this against speed, you recover integral of G on the curve, of course, taking into account the multiplicity. Another corollary, which is quite not immediate, needs some background in Riemannian manifolds. If you have a one-dimensional Riemannian manifold that is, for simplicity, embedded in a Euclidean space, so you are in some real big RDN, but some one-dimensional curve is sitting there, which is a manifold. So it goes from behind and not really self-intersecting. So there is a way to define integration on gamma of a function, and that definition is this one. So this is taken to be the definition of integrating G over the manifold gamma. So you take a partition of unity on the manifold, and on each piece you have a parameterization, a regular parameterization, and then on that piece you set this to be, you set the integral of G to be equal to this amount, and then you add them back by using your partition of unity. And then you have to prove that these are independent of the way you do the partition of unity, the way you parameterize and whatnot. Long story short, you end up with a notion of defining integral of functions on one-dimensional Riemannian manifolds. Then according to this theorem, this equals this notion. Because multiplicity is also 1, now what you have proven is that this notion of integration coincides with just integrating with respect to the Hausdorff-1 measure. And that's already an interesting fact. Okay, so please consider commenting your questions, and again, subscribe if you haven't, please. Other than that, have a great day. See you in future videos.